Hello Math 1093, this is Dr. P with Everything is Connected. In this video I want to show how we can take these two identities here, the ones that we talked about in a prior video, the sum of angle identities, and come up with some other facts about trigonometric functions. So in this video we're going to come up with, so these were the sum of angle identities. And we're going to show how we can come up with some other things, including the difference of angle identities, which we talked about in the last video, but I want to show how they're connected to these. So difference of angle identities, and then the sum of angle identity for tangent, the tangent function. And then finally I want to talk about double angle identities. So those are going to be the three things that we do in this video, and we're going to do all of this just by playing around with these two rules. Okay, so let's first talk about the difference of angle identities. So I claim that everything I'm going to do in this video can be figured out just by looking at these two rules and knowing them very well and how to use them. Okay, but we do have to use some other facts that we know about trigonometry in order to do this. All right, so I'm going to start with what happens if we take the sine of alpha minus beta. And suppose we wanted to do this, we wanted to find some expression for this, but didn't know the difference of angle formula that we talked about in the previous video. Well, there is a way of relating this. Let me see if I can pull up a different color here. We could relate this to a sum of angles. Well, how do we do that? Well, we might try rewriting sine of alpha minus beta as sine of alpha plus negative beta. And then just like that, I have a sum of angles. This is a sum of angles, which means I can now use this rule here, this sum of angles rule for sine. So I'm going to write that down. This is going to give me sine of alpha times cosine of negative beta, because the two angles I'm adding are alpha and negative beta, plus cosine of alpha times sine of negative beta. Okay, so now I have to know a little bit of trig that tells me what to do with these two things here, this cosine of negative beta and sine of negative beta. All right, you may remember from earlier that we talked about how if I have cosine of negative t, then let's just think about what that means in terms of a unit circle. Cosine of negative t, well, negative t means I go t radians counterclockwise and wind up somewhere down here. All right, so the x-coordinate at this point would be cosine of negative t. The y-coordinate would be sine of negative t. That's going to be important later. Okay, so that's if I go t radians this way. Well, if I go t radians the other way, counterclockwise, then the point that I reach on the unit circle is cosine of t, sine of t. So what this illustration tells us is that the cosine of negative t is exactly the same as the cosine of t, because whether I go clockwise or counterclockwise doesn't matter in terms of what x-coordinate I'm going to end up at. If I go this way, I'll end up at some x-coordinate. If I go this way, I'll end up at some x-coordinate, and those are the same. Okay, what about the sines? Well, the sine of negative t, that's the y-coordinate that I wind up at here. And you'll notice that's the exact opposite of this y-coordinate. So the sine of negative t is the opposite of sine of t. And I'm going to use these facts now to rewrite this expression over here. So I'm going to write this as sine of alpha times cosine of just beta, because cosine of negative beta is the same as cosine of beta. And then I've got cosine of alpha times the negative sine of beta. I don't know why I put those parentheses on the first one. I guess just habit, because I've been doing that for a while. Anyway, so that first term is sine of alpha cosine of beta. And then the second term is going to be minus cosine of alpha times sine of beta, because I'm just pulling that factor of -1 out. And what you'll see here is that I have the same formula for sine of alpha minus beta that I gave in the previous video. So that's a nice illustration of how those two facts are connected. Okay, let's do another one. Let's this time do cosine of alpha minus beta. And we can do this one a little bit faster now that we have these two facts here about cosines and sines of negative angles. Okay, so cosine of alpha minus beta, that's the same as cosine of alpha plus negative beta. And that's going to be, according to my formula up there, I'm going to have cosine of alpha cosine of negative beta plus, no, not plus, minus sine of alpha, sine of negative beta. And now I can use these. By the way, these identities over here on the right, sometimes these are called the even-odd identities. We didn't talk about this much in previous videos, but the reason we call them that is that the fact that this is true makes this an even function, cosine that is. Cosine is an even function, and this makes sine an odd function. You may remember those terms from college algebra. All right, no need to worry too much about that terminology. It's just a little connection I wanted to make. Anyway, so this cosine of alpha, cosine of negative beta, well, cosine of negative beta is the same as cosine of beta. So that term is just cosine alpha, cosine beta. And then over here I've got sine of alpha times negative sine of beta, because sine of negative beta is the opposite of sine of beta. It's turning into kind of a tongue twister. It's hard to say out loud. Anyway, if I pull this factor of negative 1 out, then I get plus sine of alpha, sine of beta, which should be the difference of angles identity for cosine that we developed previously. Okay, so those are, so the point of that is, I mean, you might just memorize both formulas at the same time, sum of angles and difference of angles, but if you can just know these two, then you can get these other two by using algebra and by using what we know about the cosine and sine function for negative angles. All right, so now let's try something else. I want to try talking about what happens if we take the tangent of alpha plus beta. That might be interesting. So what is that? Is there some way of writing that in terms of tangents of alpha and beta? And it turns out that there is a way. So the first thing that we do is we rewrite this using the definition of tangent. Definition of tangent is just tangent of something is the sine of that thing over the cosine of that thing. So I start there. Okay, so now what is this? Well, I have formulas for both sine of alpha plus beta and cosine of alpha plus beta. Sine of alpha plus beta is sine of alpha, cosine beta, plus cosine of alpha, sine of beta. Okay, that's just using the sum of angles identity. And then cosine of alpha plus beta is going to be this, cosine alpha, cosine beta, minus sine of alpha, sine of beta. Just using the formulas in this here box. Okay, now that alone is a pretty nice formula for tangent of alpha plus beta, because it allows me to put everything in terms of just alpha and beta. But now here's a question. Could I put all of this, could I put these in terms of the tangent function? And it turns out the answer is absolutely we can. It takes a little bit of clever algebra, but it is very doable. So the way that I'm going to think about this is I want to look at this denominator down here and realize I've got a sine of alpha, sine of beta here. And I know that if I want tangents, then I need to divide by the cosine of something at some point. So what I'm going to do is I'm going to take both the numerator and denominator of this, put these in parentheses so I can multiply them by something. And the thing I'm going to multiply by, now this is going to seem really strange because I'm going to make this uglier with the hope that I can eventually make it prettier. I'm going to multiply the top and bottom of this entire fraction by 1 over cosine alpha, cosine beta. I'm going to multiply that by 1 over cosine alpha, cosine beta. Now the idea here is this is equivalent to this as long as this fraction is defined here. There are places where the cosine of alpha or beta might be 0, in which case I'm actually doing something a little bit different here. But anyway, by multiplying both the numerator and denominator by this, I am not changing the value of this fraction here. So I can multiply through by this and get, if I distribute, I will get, let's see, sine of alpha, cosine of beta, over cosine of alpha, cosine of beta. And this is going to get really messy. I'm just going to warn you right now, this gets kind of a mess before it gets better. But it will get better in just a moment. All right, and then in the denominator, I have, let's see, I have cosine alpha, cosine beta, over cosine alpha, cosine beta, minus sine of alpha, sine of beta, over cosine of alpha, cosine of beta. Okay, so what do we have here? Let's just keep track of what we have that might cancel here. I can cancel any factor that appears in both the numerator and denominator and is an actual factor of both. So for example, I can cancel this factor of cosine of b. I can cancel this factor of cosine of a. I can cancel both these factors of cosine of alpha and cosine of beta. Now, once I do that, that's going to leave me with 1 there. Actually, we know this is 1 because it's just the same thing divided by the same thing. And then over here on the lower right, I don't think I have anything that cancels, but I do see some sines over cosines, and those look kind of promising. So I'm going to rewrite this as sine of alpha over cosine of alpha plus sine of beta over cosine of beta all over 1 minus, and then this is sine of alpha over cosine of alpha times sine of beta over cosine of beta. I just separated those fractions using the principle of fraction multiplication. Like imagine going backwards and saying, well, what is this fraction times this fraction? Well, you just multiply across sine of alpha, sine of beta over cosine of alpha, cosine of beta. Okay, so anyway, we're not quite done yet. There's one little step to right here, and that is I recognize the top as tangent of alpha plus tangent of beta, and that's all over 1 minus tangent of alpha times tangent of beta. And that right there is the sum of angles identity for tangent. So what this shows is that tangent of alpha plus beta is equivalent to this. And I should say again, this is as long as tangent of alpha and tangent of beta are defined, because it's possible for them not to be defined. They would fail to be defined if, for example, the cosine of alpha, which we see here, was 0, which would happen at like alpha equals pi over 2, for example. But as long as both of these are defined, this is equivalent to this. And we've shown this by doing some kind of clever, kind of nasty algebra here. Okay, one main point I want you to take away from this, even if you never derive this yourself, is this is an example of how to do a proof of a trig identity here. What we did is we just started with one side and we started chopping it up into sines and cosines, but did so in a way that maintained its value. So we're just writing down equivalent expressions throughout, and we have this chain of equalities ending with the thing that we wanted to show. Actually, we didn't start out thinking about this. We just wanted to see where this would go, but we ended up with kind of a nice expression in terms of the tangent function only. Okay, I've been talking for 13 minutes, so I'm going to stop this video here, and we will talk about the double angle identities in the next video. Stay tuned.